So in a previous video, I solved for this problem using normal tangential binormal system, but I wanted to prove to you that you could also solve this problem using cylindrical coordinates as well. So as I said, I would refer back to that other video to introduce yourself to what's provided in this problem. This is just basically a quick overview of how you could solve it in cylindrical. Like I said in the last video, once you choose the coordinates that you'll be using, it's always a good idea to then draw out the position, velocity, and acceleration vectors that we developed in class. So for the cylindrical coordinate system, we have that the radial component is just simply the magnitude of the radial component in the radial direction plus z, u, z. In the velocity direction, or for the velocity vector, we have r dot u sub r plus r theta dot in the transverse direction plus z dot u z. And for the acceleration, it's a bit complicated, but after some practice, you realize it's not all that difficult. R double dot minus r theta dot squared in the radial direction plus r theta double dot plus 2r dot theta dot. This is in the transverse direction. And then plus z double dot uz. Okay. So one way that I like to solve these cylindrical systems is if I write out columns for the different directions. So the z direction is one, the radial direction is another, and then we have the transverse or the theta direction in the third direction. So referring back to our normal tangential binormal system, when we were considering this individual here, this person's normal component was pointing towards the center of curvature. His tangential component was pointing up and to the left like so. And then the binormal was actually coming out of the board. It's the tangential component crossed with the normal component, so it would be coming out of the board. But we're solving this in the cylindrical system, and if we were to draw for this individual his cylindrical coordinates, the radial direction is actually an extension in the radial direction. Okay, so the unit radial direction is actually up and to the right. The transverse direction is in the direction of increasing theta. So that would be up and to the left. And then the z direction would actually be coming out of the board. It would be equivalent to the binormal in the NTB coordinate system. So you really notice that the only difference between the cylindrical and the NTB system is that the radial normal component, the radial unit component, is pointing up and to the right, where the normal vector, when we were using NTB, was pointing in the opposite direction. So what we should find out is that our components in our radial direction in the cylindrical coordinate system will be in the opposite direction for our normal components in the NTB system. Otherwise, the magnitude should all be the same. It's the same system regardless of the coordinates that you choose to use to study these problems. But paying attention to the positive unit directions is very important. And I find it very helpful to draw those as necessary on the diagram itself. So we recognize that this is a planar problem, that all the motion occurs on this individual plane. And so if we were to call this plane z is equal to 0, and we recognize that there's no speed and there is no acceleration out or into the board itself, then these equations actually become simpler pretty quickly. And if we consider the radial direction, we notice that the radius is 40 feet because we're looking at the passengers themselves, and because they're not moving away from the axle or moving toward the axle, r dot is 0 and r double dot is 0. So these would be velocities, or rather speeds, in the radial direction, or the accelerations in the radial direction. And as we've drawn that and circled it in red, and I'll circle it again in red, there is no component of its speed in that radial direction. He's not flying away from the center of the rotation. He's not flying towards the axle. So all of his velocity must actually be stored in that transverse component. So anywhere that you see an r dot or an r double dot in the above equations, you can cross out because they don't factor in. So what I was just saying here was that all of his speed must be stored in the transverse direction there, which is what we solved for in the normal tangential binormal coordinates. The velocity vector for our NTB coordinates is simply the speed in the direction tangent to the curve. And that agrees with what we have here for the cylindrical, that the speed for this object that's going around a circle only has one component of its velocity, and it's tangent to the curve that it's on in the direction of the speed itself, of the velocity itself, tangential velocity. Okay, that being said, we still need to solve for theta dot, which appears in this term and in the second term that I'm circling there. And once we get theta dot, we also need to solve for theta double dot as well. Well, what do we know about theta? The only thing we know about theta is that initially it's at 0 degrees, which according to our last problem, if we call this horizontal, our initial 0 position, and then at some later time it's at 30 degrees. But we don't know anything about the angular velocity, which is theta dot, and we don't know anything about theta double dot, which is our angular acceleration. We need to find those so that we can plug it into our velocity and acceleration equations above. This problem is asking us to find v and a, the magnitudes of our velocity and acceleration vectors. Okay? So in order to do that, we need to find the components of the velocity and acceleration vectors. Okay, well, we drew this when we solved this problem using the NTB coordinates, but it's equally valid. This is a wedge of a circle which relates the arc length s and the transverse component theta through our radius of curvature, or the radius of this portion of the wedge, call it r. S is equal to r theta. Now, why are we doing this? Well, we're doing this because we have information relating v dot and t, and we have information about how theta changes, but we don't have any information about how theta changes with respect to t. So we need to come up with a way to bridge the gap between v dot, t, and theta. So we start by looking at s is equal to r theta. If we take the first derivative, s dot, so s with respect to t, ds dt, that gives us s dot. Another way to write that is just simply v is equal to r theta dot. And if we take a second derivative, v dot is equal to r theta double dot. Okay, still we don't quite have that missing link, but at least now we have a relationship between v dot, which is known as a function of time, and theta double dot, which we can relate back to theta through some calculus and manipulation. So if we look and rearrange that last equation that I circled in red, theta double dot is equal to v dot divided by r. Theta double dot, another way to write that is theta dot dt, first derivative of theta dot with respect to time, is equal to v dot over r. We can rewrite this by solving for d theta dot is equal to v dot over r dt. Now we can integrate this if we were to have a relationship for v dot with respect to time. And we do have such a relationship. Over here is provided for us. V dot is equal to 4t. So in this case, d theta dot is equal to 4t over r dt. At this point, we can perform this integral because we related v dot to t explicitly. Theta dot initial to some final theta dot. And our limit of integration over here is our initial time and our final time. Now, we know that the Ferris wheel starts from rest, So theta dot initially goes to 0. And we start our stopwatch at our initial time, so we allow t naught to be equal to 0. And when we solve this equation, this integral, we get theta dot is equal to 2t squared over r. Now we have a relationship with the angular velocity with respect to time, but we're still not quite there yet because we don't have any other relationship with theta dot with respect to time. We have to integrate one more time. d theta dt is equal to 2t squared over r. Solve for d theta. This would be equal to 2t squared over r dt. Now we can integrate both sides from some initial theta position to some final theta position, from some initial time to some final time, and we're left with, well, again, remember that it starts at a position of 0 degrees, and time t is started at 0. So when we solve this, theta is equal to 2/3 t cubed over r. And if we go all the way back to where we solved this problem using our normal tangential binormal coordinates, we find that t cubed is equal to 3/2 r theta over here. And down here, when we solve for t/3, t cubed, we get 3/2 r theta, the exact same expression that we had developed using our normal tangential binormal system. We know r and we know theta. When we plug in pi over 6 for radians here, we don't want to include degrees for theta. And when we include 40 feet here for our radius, of course the time becomes the same as what we had solved in the first video, 3.1554 seconds. So now we have the period of time that it takes for this Ferris wheel to swing through that 30-degree arc. It's the same period of time regardless of what coordinate system we use to solve these problems in. The only thing left to do at this point is go back to our cylindrical system and highlight once again all the terms that we're interested in. We need to determine at this point theta dot and theta double dot. Well, when we solved using the cylindrical system, we had come up with a series of equations that related theta dot, and we can determine what theta double dot is from right here. V dot divided by r is equal to theta double dot. We have V dot. We have an expression for V dot in terms of time, and we know radius, so we can solve for theta double dot. And here, for theta dot, we know period of time, so we can plug that into our equation and divide by the radius, which is also known. So for theta dot, this is equal to 2t squared divided by r, 2 times 3.1554 squared divided by r, 40 feet. Theta, and this turns out to be 0.498 radians per second. Theta double dot turns out to be 4 times 3.1554 over 40 feet. This turns out to be 0.316 radians per second squared. This is an angular acceleration. So if we were to remember these numbers here for theta dot and theta double dot and plug them in to our expressions for our velocity vector and our acceleration vector, what do you think that we should find? Well, our velocity, there's only one component of our velocity, that's r theta dot. 40 feet times theta dot, which we solve for 0.498 radians per second. R theta dot is equal to 19.9 meters per second. This was the same speed that we determined using our NTV coordinate system. This is for velocity. There was only one component that we needed to solve for. Acceleration, there are two components that we need to solve for. One is negative r theta dot squared. The other component, this is in the radial direction. And in the transverse, that theta direction, we had a component r theta double dot. Plugging these values in, negative 40 feet times theta dot, 0.498 radians per second. We're left with negative 9.91 feet per second. R theta double dot, this is 40 feet times theta double dot, 0.316 radians per second squared. This turns out to be 12.64 feet per second squared. The acceleration is the square root of the sum of the squares of all the components. In this case, we have a radial component and a theta component. When we plug these values in, we find it equal to 16 feet per second squared. So this is exactly the same magnitude of our acceleration that we had solved using our normal tangential binormal system. The only slight difference is that notice this is a negative 9.91 feet per second. The acceleration in the radial direction is at negative 9.91 feet per second. If we go back to our normal tangential, we find that 9.91 feet per second squared is the acceleration in our normal direction. And the reason why we have this negative in our cylindrical and a positive in our normal direction is because, remember, the normal direction is pointing towards the center of the circle. The radial direction up here, which I've circled a whole bunch of times already, is pointing away from the center of the circle. So the negative 9.91 feet per second squared that we determined using the cylindrical system is actually pointing towards the center of the circle. It actually, by it being a negative value, it means it's truly pointing in the opposite direction from what we define as our positive unit vector. As far as the transverse direction is concerned, we found that its component, the acceleration, was, this should actually read 9.91 feet per second squared here. But the transverse direction, we found that that was equal to 12.64, a positive quantity. And when we solved for this in our normal tangential system, we found that it too was a positive 12.62 feet per second squared. That's just a rounding error, but the same thing. They're both positive quantities because it turns out that in our cylindrical system and in our tangential system, those unit vectors are pointing in the same direction. So of course they should both be positive based off of how we define those positive directions for the transverse direction and the tangential direction.